over to Tim Davis to tell us about cold gas properties of simulated post-starbursts. Tim.
Thanks, Chris. And I wanted to thank Katie as well for giving such an excellent review, which makes the beginning of my talk really, really simple. So thanks a lot. So I'm going to tell you a little bit about what happens to the cold gas in post-starburst galaxies, as Katie has so well introduced, and especially in simulated post-starburst galaxies. So this is something, I'm not normally a simulator, but I was sat in a quenching meeting in the Lorentz Center in Leiden and having these discussions with everyone, and we were like, oh, we really want to know what's going on with these post-starburst galaxies, why they have these big molecular gas reservoirs. And we thought, well, we could look in a simulation. And people turned to me and said, no, you can look in a simulation. So I did, and that's what I'm going to tell you about today. It's all presented in this paper here that was published in MRS this year. So we saw a version of this picture already. Gas is so important if you want to understand quenching galaxies. It's the fuel for star formation, so you've really got to do something to it if you want to move your galaxy from a spiral galaxy to a gas-poor early-type galaxy. You've just got to. And as Katie told us, the gas is expected to be consumed or destroyed here at the sort of starburst or phase here before you get your post-starburst galaxies. But is that really what's going on? So we're going to concentrate on these galaxies here for this talk. There are, of course, other ways that you can quench and go between here. This is a rapid pathway. There are other pathways that have varying importance at different redshifts and different times and different environments. But these rapidly quenching galaxies are something we really need to understand. And as Katie already told us, you can select these if you get a spectrum from these very deep Balmer absorption features. You see these things that come all the way down on the left-hand side here between about 4,000 and 5,000 angstroms. These things really pinpoint to you that you've got this big population of A stars. So if you go out and you get your Sloan spectra or spectra of any kind, and you can select these objects. And as Katie already told us, you can go out and you can look at them and you can say, okay, how much molecular gas is there? We didn't expect much, but it turns out, as we've already seen, that actually they do have large molecular gas reservoirs in many cases. 50% of these galaxies are detected, and those have greater than 10 to the 9, so more molecular gas than the Milky Way has. So these things really have to be explained. We thought these things had no star formation, so how do they have more molecular gas than the Milky Way? So you've already seen that very clearly. So, how do they do it in a simulation? We thought this is really the way to tell. If you want to trace something with time, we can't do that so well with observations yet. We're trying. But a simulation, you get this automatically. So I used Eagle for this. You've all heard of Eagle, I'm sure. It's this big simulation suite. We used the 100 megaparsec cubed volume. And we used the very fast snapshot outputs for this. Normally, when you download the Eagle simulations, you only get 28 outputs from high redshift down to redshift 0. But if you use the snapshots, you get 200 instead. So you can really study things that happen quickly, like our post-starburst. So that was crucial for this work. Obviously, there's a caveat in using simulations, and that is that cosmological simulations don't have a proper ISM. It's just the resolution on a cosmological scale is not good enough to really resolve the gas into its different phases. So what we'll use here instead of molecular gas is star-forming gas, according to the Eagle definition. So that's an important caveat that's important to understand. So if we're going to trace these galaxies, we have to go and find them. So the way we did this is we looked at the specific star formation rate versus time. So here I'm plotting specific star formation rate, so star formation rate per stellar mass.
Tim, can you stay at the podium and use the laser pointer?
Sorry.
Because then you're on the mic and screen and stuff.
Star formation rate per stellar mass here, and then look back time. So this is high redshift, and this is redshift 0. So this is an example here of a galaxy that grows quite steadily over a long period of cosmic time, and then it has some event here, starts quenching here and has a fast drop in its specific star formation rate. So we chose post-starburst galaxies to be things with a drop of at least a factor 5 in their specific star formation rate over 600 million years, which seems to make sense observationally. And we can correlate this with all sorts of things that happen in the galaxy, because you can see we know all the information in principle. We know when the mergers happened, we know when the black hole accretion rate picked up, all sorts of things about these galaxies that we can use to work out what's happening in them. So, when we do this, do we get a realistic sample? Well, it turns out that we do. You can look at their mock spectra and classify them with principal components or using the various different ways observational samples happen, and they do look like real post-starbursts. Their space density is also the same. So this is a plot here, again, of look-back time versus number density. And the red, blue, and green points here are different post-starburst selection estimators of the number density of these objects, and the black points are the simulation, and you can see that matches really quite well. These things become more and more important, more and more common as you go to high redshifts. Their sizes and masses also match quite well, although we do have a lack of low-mass objects essentially because of the simulation resolution. So, what about their gas? The intrinsic molecular gas, star-forming gas, follows this dashed line. So there are lots of galaxies with lower masses than the observed post-starburst galaxies, which are shown here in red. But once you take into account that the observations are biased, you have a Malmquist bias, you only see the bright ones, you end up with a black line that matches really quite well the observations. So intrinsically, essentially all post-starburst galaxies are expected to have significant molecular gas reservoirs, and we just pick out the 50% because those happen to be the brightest ones. So it seems that it takes time for post-starburst galaxies to lose their gas. As we've already seen, you can't just look at the post-starbursts and say they're a gas-free population, because they're not. Indeed, there's a significant time evolution in the gas fraction. So what I'm plotting here is the look-back time, but reference now to T-bursts, so when we think this quenching happened at 0 here, and then time progresses to the right now, against the gas fraction, the star-forming gas mass over the stellar mass of the galaxy. And the blue points are all of these post-starburst galaxies and their evolution from the simulation. So you can see they typically have high gas fractions, 10% or something, as a typical galaxy does, and then they fall right down to a hundredth here, over about 600 million years. But this is after the post-starburst phase has already started. The black points here are from work by Decker French, where she has been able to age date the real post-starburst galaxies and plot that against their molecular gas fraction. You can see that we match really well. I was really pleased when I saw this. I think it was great. So we really do seem to be capturing the evolution of these systems. They do become gas poor, but only over time, and only once the post-starburst phase has happened. So, why is this? How can you have all this gas in these galaxies that isn't forming many stars? So as Katie's already told you, one way to do that is you render the gas inert. You do something to it. In the simulations, we can't model the turbulent injection Katie was talking about because that's just not in the subgrid models. But we still see a difference. So here I'm plotting the star formation efficiency, or actually the depletion time of the gas, so how long it would take to completely remove it, against this time indicator where 0 again is when a post-starburst event starts to happen. So you can see that it bumbles along at a typical star formation efficiency. Some galaxies have little bursts down here to very efficient star formation at all these previous times. Around the event happening, we have a big spike in galaxies with very low star formation low depletion times, so very efficient star formation. And then you can see, even in the simulations where the subgrid models don't allow you much room in your star formation efficiency, you see that the star formation efficiency drops. And you end up with lower star formation efficiency in your galaxies around the post-starburst. The black, again, are points from Decker French and Katie's work, where you can measure the depletion times, and you can see we can't reproduce these things because this is the lowest star formation efficiency the simulations will let us go to. But we do see this difference. And the reason for this is that the gas in the post-starburst galaxies becomes less dense. Some energy has been put into it by whatever is quenching it, and what that is I'll go into in a moment, and that has caused the gas to expand, at least in the simulations. So what causes the quenching? We talked about this earlier. Well, this is an example here. So this is a galaxy that becomes a post-starburst, and this is a little, very simple movie that I made from the particle data showing what's happening to this galaxy. As you can see, this thing enters a cluster and gets ram pressure stripped. So you can see the gas exiting it as the little blue points there as it comes in, boom, stripped. So environment is very important. Ram pressure especially, we can quantify it as being a really important thing that's removing the gas in these galaxies. Mergers are also super important, of all masses. AGN are the interesting thing, because classically, AGN are put in to these sort of models to do exactly this, to quench the galaxies and quench them quickly. So are they doing anything in these post-starburst galaxies? And the answer seems to be essentially no. So here I'm plotting the accretion rate of our post-starburst galaxies onto the black hole. So this is the energy input from the black hole essentially back into the ISM of the galaxy, versus a control sample selected to match in star formation rate and gas mass and stellar mass at the moment where the galaxy undergoes its post-starburst phase. And you can see essentially, this again is plotted against time, essentially these galaxies don't really care. There's a slight increase in the average accretion rate of their black holes around their post-starburst episode, but it's really quite small, and the scatter is massive here. This is 10 orders of magnitude. So it doesn't seem that AGN are super important in quenching the objects here in our study. They, of course, can input energy when something else is going on and help that mechanism along, but certainly in Eagle at least, the AGN aren't very important. So what is important? We can quantify that. So here I show you a bar diagram. So this is the fraction of galaxies where we think the post-starburst phase was caused by a specific mechanism. You'll note these don't add up to 100. Multiple galaxies could be going through multiple things at one time, and some things we just can't tell. We've got thousands of these things in the simulation. We can't go through and look at each one by hand and work out what's going on. But we can say AGN seem to be really important, greater than 3 times the control galaxies in about 9% of the galaxies. Ram pressure stripping is at least 10%, but probably more. It's just our limit to be able to track it. But the control galaxies, 5% of those are also undergoing some sort of ram pressure stripping at that time. So about 5% of galaxies over the field are caused by this ram pressure stripping. And then mergers. Again, the control line here, you see there's enhanced merger rates in all of these populations, both for major mergers, minor mergers, and these micro mergers. And these micro mergers are interesting because we wouldn't expect them to quench galaxies. They happen all the time onto all sorts of galaxies. So the spiral galaxies like the Milky Way have micro mergers all the time and they're not being quenched. But what this probably means actually is that we're seeing group pre-processing. Most of these galaxies that have this really enhanced minor merger rate are on the edge of clusters, and they're about to fall in. Within about a gig a year, a lot of these galaxies ended up being satellites in a larger halo, but we are not satellites when the post-starburst phase happens. So I think that's probably an environmental signature as well. And the other thing we find is that major mergers are most important in causing post-starburst at low redshifts. And this is somewhat counter to some observational results, so it's quite interesting, and that's something that needs to be looked into further. So, I think I'm just about out of time, so I'll leave you with the conclusions. Post-starburst galaxies are quenching, and the gas is being removed, but it's not being removed in this phase. It's actually being removed while they're a post-starburst galaxy. And not all of it is actually removed, because some is left over to become the molecular gas reservoir of the early type galaxies, which do often have small gas reservoirs at the end of their life. So, thank you.
Thanks, really interesting stuff. Questions? Yeah, back. Run, Kevin, run.
Well, hi, Tim. Well, thanks. It was very good, interesting talk. I was wondering, so because I remember this paper, and one of the things, of course, in the simulation was that you don't actually resolve the molecular phase, right? So your gas, what you call molecular gas, is very dilute gas. It's more atomic gas, and so how does that really connect? I mean, how strong is the link that you lay out compared with observations that are actually based on molecular gas? Thanks.
Yeah, so this is clearly a problem that all the simulations face when you're trying to answer these questions about the cold gas. So there's been papers by Claudia Lagos that showed that if you use the star-forming gas, you're wrong, but you're not that wrong. You're normally within a factor of 2 of the real molecular gas mass, which when we're mostly working in log is probably okay, but I agree it's not ideal, and if there are things that are happening in these sort of merger phases that are expanding the gas, probably a lot of it might go atomic, for instance, much more quickly than the star-forming criteria in the simulations. So there's a lot of work to be done still on improving that, I think.
Thanks. Is Nikki here? Yeah, do you want to come and set up? Is there another question for Tim? Yeah, at the back there. So, thanks.
Hi, Tim. Very, very interesting. So the Eagle simulation is able to reproduce the stellar mass function, right? With AGN feedback, when you include AGN feedback. So at the high mass end, so if you look only at the high mass end of the population, if you select the subsample, what are your results? I mean, I guess AGN feedback must play a substantial role there, because we do see that the stellar mass function drops when you include AGN feedback there.
Yeah, so I mean, people like Robert are probably even better to talk about this than I am, but yeah, so I think you're right, the AGN have to be important. They're put in the simulation especially to be important. They don't seem to be important in this post-starburst galaxies. They typically, a little bit lower mass, they're typically all around 10 to the 10, the ones we pull out in the simulation. So maybe the AGN are more important at keeping the halos hot of the galaxies at higher masses once they've been through this phase.
And the statistics you showed was averaged over the full population?
Yeah, that was averaged over the full population. We did look at it as a function of redshift and things in the paper.
Yeah, as a function of mass also maybe would be interesting. At very high masses, what happens?
Yeah, so I haven't broken it down by mass, but it's an interesting point. We should do that.
Great. Thank you very much. Let's thank Tim again.